Okay, dear students, dear colleagues, ladies and gentlemen, it's a great pleasure to me to introduce Professor Paul Chaikin for today's colloquium. Professor Chaikin is coming from the Department of Physics in New York University in New York, Manhattan. Well, the picture is already gone, but we will see later on. Let me just say a few things about his career. He got the degree at the California Institute of Technology and then the PhD at the University of Pennsylvania, and the advisors were Professor Jensen and Alan Eager. And the title of the dissertation was Probing Many Body Effects with Superconductivity. So you already know here what were the interests in the first stage of Paul. Then he had a tremendous career. He asked me to be very short for the introduction, so I will try just to point out a few important points of your CV. So he started as a professor at the University of California in Los Angeles, where he got full professor in 1983, and then he moved basically to Princeton, where he was owner of Henry DeVol Smith Professor of Physics there. In between, he was consultant for several companies like Exxon Research and Engineering Company and NEC Institute in Princeton as well. And he also was visiting professor in Europe for 2 times. So apparently from your CV, I understand you have strong liaison with France. You were twice there in Paris, which is certainly very great. And now, since 2005, he moved to New York downtown, so to say, at the New York University, as I just said, and there is owner of a silver professor of physics, and he basically built up the Center for Soft Condensed Matter Research. He has a tremendous record in publication. Here I would like to mention that he wrote a book together with Professor Lubinsky, Principle of Condensed Matter Physics, and I may say that besides Ashcroft, Mermin, and Kittel, he's probably one of the most important textbooks in condensed matter in US at least. And he wrote more than 300 papers, and he was invited to many conferences and meetings. He has also many additional activities, just 2 full pages of his CV. So it's a fellow, a member of many associations and like the National Academy of Science, for instance, the American Physical Society, the fellow of the Institute of Physics, and also he was member of several evaluation committees all over Europe and also in US. I would like here just to mention a curiosity, since next year we are going to be evaluated as well at our Department of Physics in spring next year. Paul was in 2005, yes, a member of the evaluation committee of our lovely sister school in Lausanne as far as the Department of Physics is concerned. So, and he was also chairman of several conferences as well. So he has many interests in condensed matter. So let me mention at least your great work on organic materials, particularly on the linear chain Beskar salts, which were the very first organic superconductors, by the way, really a prototypical system in order to study whatever is important in condensed matter, and he did really a great work there. And then recently he moved somehow his interest towards soft condensed matter, about which the talk is going to be tonight. So thank you very much for coming to Zurich, for putting this colloquium into your very busy schedule, and we really appreciate that you are here. So please welcome Paul for his talk about classical Wigner crystals on flat and curved surface, topological defects, pleats, and classical particle fractionalization. Okay, welcome.
Thank you. It's not showing up. Just that. The last words aren't showing up. Anyway, it's great to be here. It turns out I haven't been here before, and I'm related to this place. One of my advisors was Tony Jensen, as Leonardo mentioned. Tony Jensen was a student of Bernd Matthias, and Bernd Matthias was a student of Scherer, who is here. So I'm finally back, okay, after many years. Okay, so Wigner crystals. Usually you see Wigner crystals are crystals completely stabilized by charge, and the usual context you've seen them in is typically as a quantum system, one of the many different phases you can have for electrons at low temperature. But I'm going to show you that you can also study them in a classical system, and you find that there are many interesting things that you see, both sort of classical effects, dislocations, topological defects, things like that. And finally, what I'm going to end up with is a little bit something that we didn't really expect it to begin with, which is charge fractionalization, and in fact, particle fractionalization in a classical context. Okay. The system I'm going to be dealing with are colloids. Colloids are typically micron-sized particles. In this case, they're charged. That's why it'll be a Wigner crystal. And you can study them, as shown here in the upper guy, in a two-dimensional lattice. This is a perfect lattice. And some of the things we can do, one of the reasons that soft condensed matter is interesting, is with systems like colloids, the time scales and the length scales are such that you can observe absolutely everything that goes on. The time scales are the scale of seconds. Okay, that's a typical diffusion time for a particle to move its own distance. And the size of the particles is a micron, which is easily resolvable with an optical microscope. Usually we use a confocal microscope for it. And you can image things, and you can also, with laser tweezers, as I'll show you, manipulate things. So you can take a crystal like this perfect crystal over here, okay, and with weak laser tweezers over here, you can apply a shear to it, and that shear takes the perfect crystal and creates a pair, in this case, of dislocations, which are reversibly parted here and brought back together. So some of what I'll talk about is in two-dimension, because that will introduce the ideas of these topological defects that we'll look at. But what I'm really going to be interested in is curved surfaces, such as this capillary bridge here, which has the form of a catenoid. And again, because it's a soft matter system and we have complete control over it, not only can we visualize it, we can change it. So we, for instance, can change the curvature of this negative curvature beast over here, this capillary bridge, and we can watch how things rearrange under their own, interactions. These are just charged particles rearranging, trying to make a hexagonal lattice here on that surface. And that's the sort of thing I'm going to tell you we're going to be talking about in this talk. Okay, now let me see. This is important. This is really distorted, actually. I guess I'll live with it. This is William Irvine. His last initial is out. He was the postdoc that's responsible for all of what I'm going to show you, and he's an assistant professor now at University of Chicago, where he's doing even more fabulous things. Okay, this project started out with a study of hard spheres. So people have studied hard sphere systems forever, okay? The densest packing you can make of spheres, okay, is this FCC lattice that's shown over here. The densest packing you can make in one dimension is to put spheres in a row. In two dimensions, you take those two rows and you stack them on top of one another. But if you do that, you don't get the densest packing unless you slide this one over until it fits in the interstice of the row below it. If you want to go to three dimensions, you take this hexagonal lattice that you get, you stack them on top of one another, you slip it over so they fit in the interstices, and you get this FCC lattice, which is shown over here. Here's sort of the face-centered cube. This is the hexagonal part of it. This is looking at it from the side. This has been known since fruit was discovered as the densest packing of spheres. It's been known literally for millennia. It was only proven to be the densest packing of spheres about 8 years ago by a mathematician named Hall. Okay, equally well known, okay, is what happens if you take hard spheres and you pour them into a barrel and you don't put them in one by one in the closest packing. What you get is this mess that's over here, which is known as a random close packed structure. It fills space to 64%. The FCC packs better at 74%. And the reason this is known very well, again for millennia, is because as soon as in Mesopotamia they started agriculture, they started cultivating grain, they didn't have scales yet, and so they sold grain by the bushel, by volume, okay? So if you could figure out a way to pack your grain less densely than anybody else, you could sell more grain. You could buy your neighbor's farm, you could do all sorts of things, right? So it was a very important problem. Now, this problem, although it's ancient, and although this number is known to 4 decimal places, and you can get it by doing the experiment. Of course, if you do the experiment, you have to pour the stuff in, sand, for instance, into a container, and you have to tap it many, many times. It's fluffy at first, and then it densifies, okay? You have to do that. You can do a computer simulation, but mathematicians will not touch this problem whatsoever because it's got random in the name. And random, we understand essentially to mean uncorrelated. So you can do a random sequence of numbers, you can do random points in space. But if you're going to do hard spheres and you put in that they can't interpenetrate, you've already introduced a correlation. And once you introduce that correlation, what do you mean by random after that, right? And that's what nobody has been able to figure out. So mathematically, it's ill-defined. That's with ball bearings. What does this have to do with physics? Well, what it has to do with physics is, back in the 1800s, when people knew thermodynamics and they knew statistical mechanics of ideal gases, Van der Waals said, well, what if you no longer have ideal gases? You have gases that interact, okay? If they interact, you might say it's important to get the fact that there are attractions there, but he said, no, the first thing you should do is include the fact that particles don't interpenetrate. And if they don't interpenetrate, then what you'd normally write down for the entropy of a system, if there are no attractive interactions, things like that, if there's no potential, you're only concerned with the entropy would be log V. He says from V, I have to subtract the volume of each ball times the number of balls. And if I do that, the entropy now reads log V times 1 minus phi over phi C. Phi C is the concentration, the volume fraction, at which you can no longer add anything. So phi C is 74% if you make a crystal, and it's 64% if you make something that's disordered, right? And if you look at that, what that tells you, the pressure, of course, is just the volume derivative of the entropy over here. So pressure diverges at 74% if you have a crystal. If it's disordered, it diverges at 64%. And the entropy, okay, in the region between 64 and 74% is much higher for the crystalline phase than it is for the disordered phase. That sounds weird, right? Let's do it this way. You take this hall and you fill it completely randomly with spheres. You fill this place to 64%, right? Now, and there's no motion, there's no entropy associated with that. There's no motion allowed, okay? Everything's touching, everything's jammed. Now what you do is you take each of those spheres and you put it in a little cell, okay, in an FCC lattice that fills the room. You've got 64% filling. You could have 74% filling. That means that inside each of these little volumes, inside each of these little cells, you have lots of room to move around. So the entropy of the ordered phase is higher, right? And that's true. And it says that, and this is cut off on the bottom. Is there anything to do with this? Maybe I don't need it. Well, I'll just say it. You're trying. Okay, what it says is the higher entropy, if there's no energy involved here, the higher entropy always wins. And it says the highest packing fraction determines the stable high density phase. Okay, so you want a system to test this. Okay, this is Gedanken so far. So you want to test it. And a good system to test it with are things that you make as much like ideal spheres as you have, but you have to have them small so you have enough of them so that thermodynamics rather than gravity dominates what you're doing. So you take colloidal spheres. These are PMMA, that's plexiglass spheres over here. They're plexiglass because of van der Waals actually attraction. They'll stick to one another unless you put a little polymer coating on them. So the thickness of this polymer coating is 10 nanometers and the size of the particles is 10 microns. This is like a 1% effect on the size of the particle. Aside from that, there are no interactions between them. This should be a good system for studying this hard sphere transition. And the idea is, as you go to high density, okay, you should crystallize just from the fact that they don't interpenetrate. And here's the experiment that Peter Pusey did with Van Meegen in Edinburgh in 1986. Here, they've got the volume fraction going the wrong way. So here, they've got a liquid. Okay, here they're starting to see crystal. If you make a crystal of these micron-sized spheres, the lattice spacing is like a micron, which is like the wavelength of visible light, so they'll Bragg scatter visible light. So what you see in terms of colors from these things is what you'd see if you could see with X-rays and you looked at this, which is iron, I think, which has the same structure, FCC, as these guys do. Half the elements or more crystallize FCC. So here you start to see crystal. You increase the volume fraction. This is about 50%, 53%. You still have some liquid. This is a coexistence region. Now you have all crystal over here. And then what he found is as you increase the density higher, you got a disordered phase, okay, which was at higher density than the crystal. That's why it's sunk to the bottom over here. And he said this is a glass phase. So Pusey did these experiments. They're beautiful experiments. They show you that something which is just a system of hard spheres, okay, just from excluded volume will crystallize, okay? And he agreed very well with the best phase diagram that they had at the time. This is the phase diagram that people had up to about 1995. Liquid up to 49%, crystal from 54% up, and maybe between 58 and 63, which is 63, 64 is random close packing, this glass phase. Okay, this is a beautiful experiment, right? You have these little vials that are sitting on a table. Okay, they're made of plexiglass. The whole experiment cost maybe $80, right? So in soft matter, we were really, really jealous, right? I mean, a typical hard condensed matter experiment costs a couple $1,000. If you want to do neutrons or X-rays, maybe it costs 100,000, right? If you want to do something really fancy, something maybe $1 million. We really felt bad, right? Our experiments were really cheap. So we were looking for a way to make this an expensive experiment. How do you make this an expensive experiment? Well, one way you can make an expensive experiment is you send it into space, right? Your minimum cost for the liftoff of the shuttle is $500 million, okay? So now we're getting the big leagues, right? Okay, so we send up our samples into microgravity, and we get our own phase diagram, okay? And what the phase diagram shows is below 50% is liquid, above like 50% you're starting to get crystals. Actually, when you look at how the crystals grow, they grow like snowflakes. One of the things we found out is the model at the time for how the crystals would grow is like a spherical shell growing out. That's a standard model for nucleation and growth. But there's an instability which you could actually calculate once you know it's there, which means dendrites shoot out. So that's something we found, but that's not that spectacular. The main thing we found in this experiment is when you look at all these volume fractions up through random close packing, but not above, because you can't get a sample that's disordered above there, everything crystallizes. And it crystallizes essentially immediately, okay? So after this experiment, not only did everybody sort of agree that this was okay, and people that tried to do density matching on the ground, they actually, I'll get to that in a second, didn't do very much. But after this experiment, all the theories agreed and all the simulations agreed that there's no glass phase. So now it's accepted that for monodispersed hard spheres, you have a liquid and you have a crystal, but you don't have a glass, right? Okay, I should mention, the only sample that survives, so in when you send this up, the reason you send it up in orbit is there's microgravity, things don't sediment. On reentry, it gets buffeted like crazy. 50 Gs RMS must drive the astronauts nuts, right? It just shakes like crazy. The only sample that survived was the sample that was supposed to be a glass on the ground. Okay, so now we have this sample back in our hands, and the question is, maybe we screwed up. Maybe we sent up the wrong concentration, right? So what are we going to do? We can't remelt it. If we remelt it and it doesn't recrystallize, it's $500 million to get it to crystallize again, right? So what are we going to do? So the answer is, what you do is you melt half of it. Here's a stir rod. The bottom of this tube is down somewhere over here. Here's a stir rod, which you use a magnetic stir rod. You melt the bottom half. You leave the magnet there. If you have a liquid, it should sediment. This is a year after we mixed it. The magnet is still there, which means it's a glass. That is, it's something with no long-range order, but a shear modulus, but a rigidity, so this thing doesn't fall through it. It's not just viscous. And above it is the crystal over here, which grew in space. And this crystal slowly grows into here, which shows you this equilibrium phase. Okay. So this actually was a discovery. It was actually, we sent stuff up into space. We actually found something out, okay? We didn't bring back gold or platinum or diamonds or anything like that. We brought back knowledge, and that's what you're supposed to do in an experiment that you do in space. Okay, so now people said, well, that's interesting. We should check it out. But we don't want to spend $1 billion again or $500 million again. So what we will do is, in order to make these samples, what you do is you take the plexiglass spheres, and if you really want to be able to see into them or do scattering from them, you don't want them to have a big contrast with the fluid that they're in. You also don't want them to van der Waals attract. If you want to get rid of van der Waals interaction, you know, is fluctuations in the electromagnetic field, right? And it's completely quantum mechanical. But the way you can get rid of it is if the dielectric constant, okay, of the medium that you're in is exactly the same as the dielectric constant of your spheres, there's no van der Waals interaction. It's the same medium, right? So what you do, and it turns out the main part of van der Waals comes in the visible, so what you end up doing is index matching your sample, index matching your fluids. You take two fluids, you mix them to get the same index as the spheres, okay? So you've used two fluids. If now, in addition, you want to density match them, if you want to density match them, you have to have a third component that you add in, so you can both index match and density match with three of them, and then you vary temperature to finally do it. So a lot of groups tried this, and what they ended up with is, for instance, something that looks like this. These are 1 micron spheres, PMMA spheres again, and they form a nice crystal like this, but the spacing between them is 30 microns. So they're nowhere near touching one another. So what happened is, in adding this other component, they no longer had hard spheres, they had charged spheres. And the Coulomb repulsion between them was giving you this Wigner crystal over here. This is a 3D Wigner crystal. Okay? Here's another one over here. Now the problem was, the groups that were trying this, they tried very hard to get rid of the electrostatics. Sometimes they could, and sometimes they couldn't. They were after hard spheres, after all. Turns out, Coulomb crystals were known before this in colloids. They're fairly easy to make in a water system, instead of in cyclohexylbromide, which is what this was in. So some of this was done by the group in Utrecht, and I was at Princeton at the time, and we were had the right machinery to do the electrostatics, to do dielectric spectroscopy on these things to see what's wrong. And the problem was, sometimes they would see this effect, and sometimes they wouldn't. And how big these Wigner crystals were, what the lattice constant was, depended on the day of the month and everything like that. So they sent over a student, Miriam Lunison, to our lab to do these experiments. And I looked at these, what she was finding, and I saw that, it changed from day to day and with the cycles of the moon and everything like that. And I said, okay, so this reminds me of when I was doing hard condensed matter physics, and I was making samples. And one of the things that you never can control very well unless you really take precautions is humidity, right? And humidity can really screw you up. If you're evaporating a sample on a slide and it's humid, you get a completely different answer than if you evaporate a metal when the humidity is low. So it's hard to control humidity. The thing you can do that's easiest is add water to the system. Right? You add water to the system and you see what it does. So first, I should say that what's happening in the system is the particles are charged over here. They repel one another. The charge on each particle, they're 1 micron particles. The charge on each one is something like 100 charges. And the interaction between the particles is not a direct Coulomb interaction because these counter ions, everything that you deal with, including your body and everything, is charge neutral. You know that. If you don't have charge neutrality, the forces, electrostatic forces, are enormous. They'll blow you apart. Okay, so this is charge neutral. So if I say these guys are charged, what I mean is they're charged, but the counter charge is in solution around them. That gives you a screened Coulomb interaction. It gives you a Kawa potential over here. And this is exactly the same thing you get in a metal. The only difference in a metal is you don't talk about ions, you talk about the concentration of electrons. And instead of talking about temperature here, you talk about the Fermi temperature. And this is Thomas Fermi screening. And here it's the same thing, except you have KT disordering you, and it's ions here rather than electrons. But it's a screened Coulomb interaction here, just like you would have in a metal, between charges in a metal. Okay, and the problem is if the screening length is too small, okay, then you won't get this long-range interaction, right? You die off exponentially. So what's obviously happening in this system is that the screening length was very large. The idea of what water would do is the following. The particles were suspended in an oil, cyclohexylbromine, dodecane, things like that. It has a low dielectric constant. If you put water next to it with a dielectric constant of 80, the ions, okay, would rather be, according to electrostatics, they have an energy minus epsilon e squared over 2. They would rather be in something with a high dielectric constant. So the ions here should suck over to the water. The water should just clean out the ions from the oil system. And that would explain why suddenly the screening length was very large and why we were getting this effect. So let me see. So here is what happens. You put the water in. Here's a drop of water in the system that I showed you before. When you put the drop of water in, you always get this Wigner crystal over here with a very large screening length, with a large Coulomb interaction, screen Coulomb interaction, almost unscreened between the ions. But you get something else as well. First, here's the water droplet. You have a depleted zone over here where there are none of these colloids, and you have right next to the water a monolayer of the colloids, right? This was completely unexpected. We didn't understand this. The fact that you have a repulsion here between the water droplet and the colloid over here suggests that the water droplet is charged. And it's charged with the same charge as these colloids, and that's what's repelling them, okay? If that's true, and it turns out it is, it's because I'm just a physicist, and I don't understand chemistry. And to me, the interaction of an ion with water is minus epsilon e squared over 2. But any chemist will tell you, no, that's part of the story. There are also hydration energies and the configuration of the water around the ion, And if you look then at the literature, you find, although all ions like to be in water, the hydration energy of protons is much higher than negative ions, like OH minus or bromine. So although the water sucks all the ions out, it preferentially sucks protons out, and that leaves it positively charged. Well, that's kind of interesting. That doesn't have anything to do with the colloid. That's just a property of water and the oil, okay? So if that's true, we should just be able to put water in oil, and the water droplets should repel one another. So we did that. We took the oil, we put a drop of water in it, and we shook it up. No surfactant, no nothing. This is called an emulsion when you try and mix oil and water. You guys know oil and water don't mix. That's why you have salad dressing, and you have to add something to the salad dressing to disperse it. That's usually a surfactant, okay? One side likes water, the other. This is no surfactant, no nothing. You shake it up, and you get a Wigner crystal, a charge-stabilized crystal of water droplets in oil with nothing else. See? Hexagonal part over here. You can see that, the repulsion here. This is just water and oil shaken up. Okay? This emulsion, which is charge stabilized, it's stabilized by the repulsion between these, lasts a year, more than a year. It's a very stable emulsion. Okay, so that's part of the puzzle. That's the depletion layer. This is the way a normal emulsion works. It's got surface active groups, some of which like oil, some of which like water. But in our case, we didn't need that. We just stabilized it like that. You can do water in oil, you can do oil in water, you can do water in oil and water. Well, I'm not going to go through that. That's not the main point of the talk. Okay, and even you can do that, and it shows you that these guys charge, and charges are really strong, right? They really can crystallize even droplets of water in this thing. Okay, now what about this guy over here? What about this? So now we know the depletion. We know that this is high because you've sucked most of the ions out. This is positively charged, that repels over there. What about this layer over here? If you repel the colloids from the surface, what's that guy? That was puzzling for a while. Okay, so you can control that a little bit. I won't talk about that. What it is the water has a higher dielectric constant than the oil. Just like the ions are attracted to the water, the colloids are attracted to the water because they see an image charge in the water. It has a higher dielectric constant. If you like, it's a conductor. Remember in freshman physics, somebody told you, you take a metal surface like that, you put a charge over here, it attracts to the metal surface because it sees an image charge there. Okay? These guys see their image charge. If I have a flat metal, it looks like this. You see directly image charge equally distant away. If I have a conducting sphere, then I see an image charge. It doesn't have the same charge, and it's not equally spaced. It's spaced with this distance. In any event, it sees an attraction from the image charge. Okay? That interaction, if this is the same charge, if the droplet has the same charge here, you get a repulsive interaction. But you also get an attraction of the charge over here with its image charge. And if I bring them close enough together, because the interaction between the sphere and the charge is between the center of the sphere and the center of the charge, and between the image charges is how close they get, and that can be very close, the image charge always wins. So you'll get something where at large distances, it's repulsive. At short distances, it's attractive. And that's what gives this to you. And I thought this was a fabulous discovery. Absolutely amazing discovery. It's in chapter 1 of Jackson. Chapter 1 of Jackson tells you, you charge a sphere, you take a like charge, okay? They'll repel at large distances. If you bring close enough, they'll attract. Always. They'll always, close enough, they'll always attract. So that gives us a monolayer now of colloid, okay, above the water in the oil. It doesn't go in the water because it's plexiglass. It has some charges on it, but it's plexiglass. Plexiglass doesn't like water. It's very hydrophobic. It won't go in, okay? So we have a really cool system now. We have a system where, where I've got water in whatever shape I want it, a water droplet, a flat water surface, whatever, a monolayer of particles which are charged and repelling, and nothing nearby above because of depletion. It's a really clean system for studying two-dimensional interactions here. Okay, So I won't go through this. This is confocal microscopy. This is laser tweezers. Laser tweezers work sort of the same way as what I just told you. In this case, what you do is you make the field very high in one region, and the energy minus epsilon e squared, okay, is still a negative attractive interaction. This thing just tells you the particle with the dielectric constant wants to go where the electric field is highest. It's highest in the focus of an optical beam. It's an AC electric field, but it's highest there. We do something a little bit different than usual. It turns out when you trap something with optical tweezers, the particle wants to sit where the electric field is highest, but there's also a photon pressure pushing it up. So we come with both directions to cancel that out. And then you can trap anything. So we have a system where you can have laser tweezers coming from the top, laser tweezers coming from the bottom, and from the bottom, you can also do confocal microscopy, so you can watch what you're doing while you're manipulating. I'm not going to go through what the system looks like. Here's what the system schematically looks like. If it's flat, we just take a cover slip, we put a thin layer of water on it, we should have a 2D crystal over here, we should have a depletion region, and we should have a 3D crystal over here, and this is what it looks like, right? So that's a confocal image of it. The 3D crystal over here has some gradients in it, so it's not so nice. The depletion layer is here, and here you can see a nice 2D lattice that forms there, right? And you can even see here, let me see whether I can do this again. You can clearly see it rotating there. You can see the rows, and you can also see, for example, that there is a defect there. That's what we're going to be interested in. You take these images, you just focus on the two-dimensional plane there. It's going to look, this is up here to remind you that although it's going to look like I'm doing simulations, this is data, okay? Here's what that looks like. I think this is a different image, but in any event. So this is what you see. You threshold this guy. You use software to locate the centers. You can locate the lattice. You find the neighboring particles in the lattice. You do a Voronoi construction, Delaunay triangulation, and then a Voronoi construction to find out the coordination of each guy. You expect a hexagonal lattice, and you get a hexagonal lattice here. You look at the orientation to see whether there are strains in the system or whether it's a nice uniform crystal by coloring according to orientation. So if it's green over here, then this edge of the hexagon is up. If it's blue over here, then this edge of then I'm parallel over here, and this edge is sticking out. That vertex is sticking out. So that's how you label it. This is a nice uniform crystal, except that over here, I have a defect, a topological defect. You can tell it's a topological defect many different ways. One is what differs over here from the rest of the lattice is here, all particles have 6 neighbors. And over here, this one has 5, and this one has 7. They're called disclinations. The two of them put together make what's called a dislocation. A dislocation in a hexagonal lattice has 2 extra rows of atoms coming out like that. A topological defect is topological because, well, for one thing, it's hard to get rid of. You have to cut the system out to infinity. But it also means that you don't have to see the topological defect to know it's there. You can tell that it's there by making a covering surface. The covering surface in this case is done by doing a walk around the particle. So, for instance, I take 3 steps this way, 3 steps this way, 3 steps this way, and then I repeat it. 3 steps at that angle, which is the opposite of that, 3 steps that way, 3 steps, and I close it. It comes back. If I do the same thing over here, I'm missing something. That's called a Berger's vector. And doing this construction, even if I don't look at this region, I could do this anywhere out here and it'd be missing this arrow. That's a Berger's vector, and it characterizes the dislocation, which is a topological defect. You guys know topological defects from lots of things. A charge is a topological defect for an electromagnetic field. You know that you can tell that it's there whether or not you see the charge by making a Gaussian surface and integrating over it. That's the covering surface in that case. So this is the same thing, except in geometry. These guys, which are disclinations, which are the 5 and the 7, are in flat space very, 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 very costly in energy. Why? Because if I cut out a wedge here, if I make this a 7, I add 60 degrees over here. That means is if I go out from here, okay, I'm doing something that's increasing with distance. Okay, the strain is actually increasing with distance. That means what this costs me, if I integrate it over the whole system, is its integral of r dr, so it's r squared. Okay, and that means it goes with the size of the system squared. The same thing is true if I cut this guy out. If I put this topological charge with this topological charge, the 7 and the 5, I cancel this out to lowest order, and I get a dipole, which is the dislocation we're looking at. That has a strain field that dies as 1 over r, and which integrates to log. Okay. These guys are very important for typical crystals because they give it plasticity. That's why they were invented. They were essentially invented by G.I. Taylor, who's a really great guy who does, he's known lots for his hydrodynamics. But what they do is they mean if you want to shear a crystal has shear rigidity. So a fluid, you shear it and it just moves and it doesn't come back. A crystal, you shear it and it comes back. But if it has dislocations in it, like this plane over here, then what happens is I can shear it like this, and all I do is I move this guy over, and I move it over further, and I move it over further, and I release it, and it doesn't come back. So it essentially, these dislocations tell you the difference between something that's liquid and something that's solid. They give you rigidity. And two-dimensional melting is completely about whether these dislocations are bound or not. The same thing happens for superconductors. In superconductors, what plays the role of the dislocations are vortices. If the vortices are unpinned, you're not superconducting. That is, you get a resistance. If they're pinned, okay, then it's rigid, and you get a superconductor, and the phase is locked. Okay, here is a dislocation that is simply undergoing thermal gliding over here. With optical tweezers, we can do other things to these. For instance, I can just take the crystal and strain it. If I strain it enough, I can take this region, which is a perfect crystal, and this was in the first slide as well, and I can create from it 2 dislocations. Now, topological systems not only have this property, they have a covering thing, they're conserved quantities. Okay? If I start out with no dislocations in the system, no Burger's vector, I have to get the sum of them if I create 2 of them so that the Burger's vectors cancel. Okay? So here I have to create 2 opposite ones. That's what I'm doing over there. They also, in a hexagonal lattice, react. That is, this Burger's vector is equal to this one plus this one. So I can take one dislocation there, and moving a set of optical traps over them, I can fission it into 2 dislocations, which move away. Okay. One of the things I should have said back over here is this motion, where the dislocation moves just by reassociating this with this and moving over, this is called glide, and that's what dislocations can do easily. Moving up like this is called climb, and that's next to impossible because it means I have to take a whole sheet of particles and move them essentially out of the crystal, right? So what happens if we present, did I have this here? Let me see what I've got. They're also going to give you grain boundaries. What time is it? Is there a clock around? I have half an hour left? Half an hour, 30 minutes, okay. Then it depends how quickly I should go. Dislocations also give you grain boundaries, which is what's shown there. But this is what I wanted to show. So what I'm going to do here is I have a single dislocation here, and the dislocation has these extra rows which are going out here. If I dilate the crystal in this region, the dislocation will want to move that way, right? Because it's got some extra density, so it wants to fill in where I've lowered the density. But this direction is climb, and it can't climb. So when I start expanding the crystal here, come on. It's got to figure out what to do to relieve that. So what it does is, as I do that, it reacts, as you'll see in a second, and glides, right? So you can study all sorts of things like this. I'm not going to do too much more with these. Oh, this is kind of cool. Okay. I have to do this for several reasons. Okay, so what I'm going to do, let me see, can I stop this movie? I should stop this movie for a second if I can. Okay, this is kind of cool. So it turns out in both crystals, so in hard condensed matter, I used to do charge density waves, among other things, which are like Wigner crystals to some extent. Okay, a big question always is what disorder does to all of these things, right? Now, if you take a perfect lattice and you put a disordered potential on it, okay, the lattice is going to distort, okay? And if the lattice is free to move, the whole lattice can move as a whole. If there's no potential on it, it's translationally invariant. But if I put disorder in, I can pin the lattice in different regimes. And this phenomena is a very important phenomena, and it's known in charge density wave systems and charge systems like that as Lie-Rice domains, that Rice, okay? And in superconductors, it's known by something else. In that case, you have a vortex lattice, and you pin the vortex lattice. And there it's known as Larkin domains, or Larkinov-Shinnikov domains, right? Okay, so you can do that with this, and you can watch what happens to the lattice as you introduce disorder, in this case, a potential that's just put on by the optical tweezers. So those are very weak tweezers, and you can see that this lattice is breaking up. It's no longer perfect over here in the region here. It's breaking up into domains over here, okay, which are taking advantage as best they can of that disorder potential, right? And in studies that we're doing now, you can take this whole thing and put it in tweezers and see whether it's pinned or not, and watch the motion of it. And you turn it off, and they just heal, right? So there's lots of really interesting physics that happens with this. This was actually really cool, but I'm not going to go on with it very much, because it tells you something about the intrinsic property of dislocations, or about plasticity in solids, which is that it's irreversible. What we're going to do here is take a perfect region of the sample. We're going to grab it like this and twist it, and that should make a domain. A domain is something with a different orientation, and it will be a grain. It will have a grain boundary around it. And you can actually watch the grain boundary form as you grab it and you twist like that. It creates dislocations. The dislocations make a grain boundary around it. Now it's going to go back, and here it's rotated by 60 degrees and should be perfect again. So you might have expected that they would annihilate. Now we're going to rotate it back, and you might expect, at least when you rotate it back, that it should annihilate. But the answer is, it turns out, the angle between two regions of a solid depends on the density of dislocations. So if there are no dislocations, the orientation over here and the orientation over here are the same. If I have a few of them, I rotate a little bit from here to here. If I have 30 degrees between them, then I have to have the region completely surrounded by dislocations which are touching, because the maximum rotation is 60, okay? So now what you expect is, I rotate this way, I'm going to be at 30 degrees completely surrounded. Now when I rotate back, they should annihilate. But that's not the only thing they can do. They can decrease the density another way. They can decrease the density by moving out instead of annihilating. And that's what they did here. And they leave you with those dislocations, instead of in this region, over there, over there, over there, and over there, and over there. And that is part of the plasticity, the fact that the motion, when you have dislocations, is irreversible. And we can study that and stuff. And I won't go through that. That's a study that we spent a lot of time, but I won't do it. Okay, because what I really wanted to do is to go to curved surfaces. Okay? Because since it's on water, and you can get water in whatever shape you want, you can do curved surfaces. Curved surfaces are intrinsically more interesting than flat surfaces. Here's a confocal image. This is the kind of thing we do. We just track this guy. You can see where all the particles are. You can watch them move. You can do everything just with this confocal microscope. Okay. When you're on a curved surface, these disclinations, these 5s and 7s, which I told you you just shouldn't see on a flat surface, suddenly you see them, okay? They're there. And they're there because topologically they have to be there. Now, you guys know that because you've seen soccer balls, right? Soccer balls have exactly 12 pentagons on them. What I didn't know before I started this study is I thought soccer balls always had 12 5s on them. It turns out that FICA, or whoever's in charge of soccer, read Buckminster-Fuller's paper, and they thought that Buckminster-Fullerene, okay, no, it was before that, they thought that his geodesic dome was really cool. And so after that, they made soccer balls with 12 pentagons in them. So it really came from Buckminster-Fuller, okay, that you have this, okay? Now, why are there 12? Okay, so Euler and Descartes, I think, and Poincaré, I think, told us that if you have a closed object, okay, that it can be, if you have an object, a three-dimensional object, it can be characterized by an Euler characteristic, which you can see here for any closed object. Any topologically equivalent object has an Euler characteristic, which you can get by summing the vertices minus the edges plus the faces. It equals 2. Here's a tetrahedra. 4 vertices, 6 edges, 4 faces, okay? 4 minus 6 is minus 2, plus 4 is 2. Cube, 8, 12, icosahedron, okay? All have 2, okay? It should be true for any closed object. This is a sum that you have to have. Suppose I take a sphere and I want to cover it with hexagons. Can I do it? It's also got to obey these rules. So I look at it. Here are my hexagons. So I look at a hexagon. Here's the decomposition of a hexagon. Here's the way I'll do the counting. I look at this vertex over here. Okay? There's one vertex. From that one vertex, there are 6 edges. The 6 edges, however, are shared between 2 vertices. So I have 6 over 2. There are 6 faces, but they're shared with 3 vertices, so it's 6 over 3. I sum this up, I get 0. So if I cover the surface of the sphere with hexagons, I'm going to end up with 0 Euler characteristic, which cannot be. It's a topological rule. Okay? So what do? What I do is I add some 5s. Same counting. This is a vertex. It's got 5 edges divided by 2, and it's got 5 faces divided by 3. I add those up, I get 1/6. Each pentagon contributes 1/6. Okay? I have to end up with 2. I need 12. Right? That's the way it works. Right? Okay, that's all there is to it. Okay. Now, this is true for a closed object. Suppose I don't make it my closed object. What I can do is I can do the same thing. I can take the face off, the top face off the cube. I've reduced the number of faces by 1. I haven't done anything else. So the Euler characteristic goes to 1. That's true for any topologically equivalent. Any way I distort this, as long as it's got 1 edge on it surrounding a surface, I have to end up with 1. That means if I take off both, I have to end up with 0. I've taken off 2 faces. So this guy is if I just put the tiniest hole in a sphere, or if I make a disk, all of those have Euler characteristic 1. So I'm going to have to sum up and get 1. Okay? Here, when I sum up either for a cylinder or for a disk with a hole in the middle of it, I have to end up with 0. But now there's something else that I have to tell you. If I'm in bulk, what we found is a pentagon gives you a 6th plus 1/6. A hexagon gives you 0. You can believe me, we can just do the counting again. A heptagon gives you minus the 6th. The actual counting is 6 minus n over 6. But if now I don't have just the surface, but I have an edge, I have to worry about what happens on an edge. And the answer is, if I'm on an edge, if I'm on a boundary, if I have 4 neighbors, okay, it counts as 0. If I have 3, it counts as a sixth. And if I have 5, it counts as minus 1/6. And you can convince yourself that's true because if I cut out this triangular hexagonal paper over here, you can see there are no defects inside. They're all hexagonal. But on the edge, I've got 6 of these guys, and each of them is worth a 6, so this has a characteristic 1 just like it's supposed to. And this guy has 6 on the outside and 6 5s on the inside, so it's going to have 0, which is what it's supposed to. And now the question is, if I make something like a dome, I now have to worry whether, up to now there's no question. If I have a sphere, I have 12 5s. Okay? If I have a disk, I have 6 3s on the edges. But now if I have something like a dome, which both has a surface and an edge, where do they go? And that's no longer a question that's strictly given by topology. Topology tells me the sum has to be 6, but it doesn't tell me where they have to be. They could be on the surface, they can be on the edge. That depends on energy. Okay? So now I should do a little bit of this. Three-dimensional objects, surfaces, have curvature. Curvature, there are 2 kinds of curvature. One's mean curvature, one's Gaussian curvature. Gauss said the only legitimate curvature that there is the curvature that you measure if you're on the surface, not if you look at the surface from outside. How would you measure curvature on a surface? So what you do is you draw yourself a circle with a certain radius, right? And if the circumference of the circle that you draw with that radius is 2 pi, then you're in flat space. If you're on a sphere, okay, and you walk down from the pole, okay, and you draw a circle, if the circumference is less than 2 pi times that radius that you've walked, you have positive curvature, and if it's more, you have negative curvature. So for instance, you might think that when I roll this up like that, it's curved, but I clearly haven't changed the radius. I clearly haven't changed the circumference of that. If I make a cone, I also haven't, right? Is that clear to everyone? That I haven't changed the circumference of that circle, right? Everybody buy it? Okay, I hope you buy it. In any event, okay, but Gaussian curvature like that, there's another way of writing it in terms of radii of curvature, and a surface has 2 radii of curvature. If I have a sphere, the radii of curvature is the same. If I have a saddle, there's a radius like this and a radius like this, and they're in opposite directions, so a saddle has negative curvature. These defects, these topological defects that we're talking about in a plane, okay, are sources and sinks of curvature. Here's a hexagonal sheet in flat space, right? If what I do is I take this and I get rid of 60 degrees like this, right? In flat space, this just distorted the hell out of the surface. The strain fields were enormous. They went like R squared and stuff like that. Here, I haven't strained anything. All the lines I've drawn here are exactly the same. But I have something which is no longer flat. And it's got positive Gaussian curvature. If I go down from here a certain radius and I go around, when it was flat, I had 6 sides. Now I have 5. The circumference is less, right? This is a source for curvature, a source or a sink for curvature. Suppose I do the same by adding. So here I add 60 degrees, right? That's all I did. I put a paper clip over here to hold it together. And what I have is something with curvature like that and curvature like that. I have something with negative curvature, which is a saddle, And if I go around the circumference, I have 7 sides, so it's bigger, right? So I'll pass these around so you can play with them. Okay, this is better. Usually when I give a talk on packing and stuff like that, and I talk about experiments that we did on chocolate, I give out M&Ms, but you'll just have to settle for this. Okay, so this is what they'll look like on a curved surface. This is a 5, this is a 7. They contribute pi/3 of Gaussian curvature. There's a theorem, which is called the Gauss-Bonnet theorem. The Gauss-Bonnet theorem says the integral of the curvature is an invariant. It's 2 pi times the Euler characteristic. So for a sphere, okay, I have to end up with 4 pi worth of defects. And if this guy gives me pi/3, okay, that again gives me 12 of them. This is another way of counting it. Okay? There's another thing you should know about curvature. If you've got a curved surface, parallel lines in flat space never meet. Parallel lines in curved space, if there's positive curvature, they converge. If there's negative curvature, they diverge. Okay. Now, this thing is a little bit weird. This is something I built from these Chinese Lego things with magnets and rods here. This is a 7, and this is a 5. You guys all see that? This guy is a plane here, and when I put these together, if I want to make it, just like I showed you here, that if I let myself relax from being two-dimensional, I can make something with these topological defects in it, which doesn't have any strain energy. If I do the same thing with 2 of them together, if I put them 2 together, I get something here which is a dislocation, but there's no strain because all of these rods have exactly the same length. What I have to pay instead is this plane has a step in it, and I step up to this plane. And you can see it here. You can see this line goes straight through, this line goes straight through. Here's the extra line of atoms or of balls. And there's another one that comes out over here. This will come later as something that's kind of cute, I hope, that you'll see. So the first question is, we want to know when we make domes. So we know that you have 12 5s, 12 pentagons on a sphere. Now I want to make a dome. I want to go from a disk that's flat, where I know there are 6 on the boundary, and I want to start inflating it until all I'm left with is a little patch at the bottom, and I essentially have a complete sphere. I want to know how many are on the edge and how many are on the surface. So I'm going to look, is at how many disclinations there are, the total disclination charge on the surface in terms of the integrated Gaussian curvature. And what you might expect, for example, is that when it's flat, there are none on the surface. When it's fully blown, there are 12 on the surface. That means there has to be -6 on the edge there, but that's okay. I'm only counting the ones on the surface. And you expect, for energetic reasons, that I'm just going to get a straight line here. And essentially what you find is you get something that looks pretty much like a straight line. Okay? That is, when I have a hemisphere, which is over here, I have 6 on the surface and none on the edges. Okay? It turns out that there's something that's really, really super cool that David Nelson and Mark Boeck pointed out a long time ago, which is, here are a bunch of hexagons. There are no disclinations there, right? There are no disclinations in this, right? I put it down on the table, which is on the Earth. The Earth is curved. It's a sphere. There's supposed to be disclinations here, 12 of them, right? But pretty much, okay, locally, this is flat, right? And flat doesn't want to have these disclinations. They cost a fantastic amount of energy, right? So what do you do about it? It's going to cost you a lot of energy. So here, somewhere over there, I need a disclination. It's going to cost a lot of energy there. What am I going to do? So these guys figured out you can do something really clever. What you can do is you can take pluses and minuses. Remember, these are like charges, right? If you want to screen a charge, what you can do is you can arrange positive and negative charges around it to screen it. Positive and negative charges together are dislocations, so you can screen a disclination by having strings of dislocations emanating from them. And that's what they called scars. And so when you get big, what it depends upon is the lattice spacing compared to the radius of the sphere. So here what you see, for example, is, what do we see here? 5, 7, 5, 7, 5. There's one extra 5 here, but it's got 2 dislocations on either side of it to screen it, right? And that's the way you end up not costing so much energy if your surface is almost flat, given the requirement that you have to have disclinations. It's a topological certainty that you have to have dislocations. Okay, so here's one of our bigger ones. Here are our scars. We actually have a lot of really good data on that. Okay, now, people studied spheres. Actually, the only thing that people studied up to the time we were doing this is spheres. They didn't even study domes, so the domes were already new. But the thing I really like is negative curvature, negative Gaussian curvature. For one reason, because there's nothing like a sphere you can make which has constant negative Gaussian curvature. The closest you can make is the pseudosphere here, which you can't embed in a three-dimensional space. This is the closest you can do to it, and it has to go off to infinity to close, and there's a discontinuity in slope on this edge over here. That's the best you can do. But otherwise, aside from here and the fact that it goes to infinity, this has constant negative Gaussian curvature. We can't do that, but we can do these capillary bridges. Okay? And these capillary bridges that we can make, the way you make them is you've made a dome just by putting a drop of water on a slide. You come down with another slide and you touch it, and the drop comes up and wets the other slide. You have a capillary bridge. And now you can squeeze it or expand it or do what you want with it. These guys should have 5s or 7s. Negative curvature. What should they have? 5s or 7s? 7s, right? So you look at this guy. Oh, this thing just tells you, by the way, that this thing doesn't have constant negative curvature. This actually shows you what the curvature is. The negative curvature is highest, in the, come on, I blew it, is highest in the waist over here. Okay, but here they are, and right at the waist, the green guys here are 7s. And that's sort of the first time that anybody's seen 7s, so that's kind of cool already. Okay, now, you can make lots of these guys, lots and lots of them. Now you want to do the same plot. You want to see whether the number of 7s you get goes with the integrated Gaussian curvature. You want to know whether it's going to be a straight line like this but going negative. Does it go like that? Okay. You do the measurement. Huh? It's way out here. Looks completely different. Something's wrong, it looks like. Maybe it's because these guys are cylinders. They have Euler characteristic of 0, not 1, like the domes did. Okay? Well, what you can do is you can squash them, and you can make them, you can squash these guys together, and you can make barrels, which also have Euler characteristic 0, because they're cylinders. And you can see what happens there. And I'm not going to go through it very much, but those guys just fill in. So they're just like that. So we looked at this, and we drew this line, and we said, we've got a rectifier of topological charge. Looks like a diode. So if you guys need to rectify topological charge, we can do it for you, right? Okay, but the cool thing about soft matter is you can make a movie. And you can try and figure out what's going on by looking at the movies you make. Okay, so here's a movie of a stretch of this guy. Now, you look at this movie, and you're not going to get much just looking at it. On the other hand, you can do your triangulations on it and see what happens and watch how things evolve. And you see there are essentially no 7s in the middle right now. And at this stage of the game, what we have, in fact, is no 7s in the middle. But we've got these things which aren't really scars. Of course, scars were lines of dislocations that ended in a disclination, and these guys don't. These end on the surface. But what these guys are doing is they're lines of dislocations which point toward the center. So they're trying to get the 7s toward the center, okay? But they're not making separate topological charge there. They're just pointing toward it, okay? As you stretch more, what happens is they break off and they give you topological charge in the middle, and they retreat toward the boundary. And so that's how these guys arrange. But in between getting them, so there's a threshold before you get them, in between getting them, you had these lines of dislocations. And it turns out, after a while, we figured, let me see, am I wearing the right pants for this? I'm not wearing the right pants for this. That's a shame. What we discovered, again, about 5 millennia too late, okay, was pleats. Because a pleat is something you do if you take a fabric and your waist is smaller than your hips, and you want to add material as you go down. So if you add material as you go down, okay, that's like having a dislocation, which as you add dislocations, you're adding material as you go down, right? And so these guys are pleats. They're the equivalent to pleats, okay? Like that, okay? Now, how much time do I have? Not much, right? Okay, so you can see how these things come in. One of the things that's interesting is, I won't go through that, is this. So, if you add pleats, okay, it turns out if you have equally spaced pleats, okay, what it'll give you is something which is a cone. I don't know whether that's obvious to everyone. It'll give you something that's a cone because you're adding material constantly as you go down. If you're adding material constantly as you go down, that's just what a cone does, right? And a cone like that doesn't have any Gaussian curvature. That's what I was trying to convince you of before, okay? And if you like, the analogy is the following. If you have dipoles, they give you a polarization. If you have a uniform polarization, you have a uniform polarization. If you have a gradient in polarization, you get polarization charge, right? That's, for example, what happens in a capacitor. You have polarization, the capacitor material ends, and you have surface charge, and you have surface charge on the other side. So if you have gradients, okay, you can get charge, which is like topological charge, which is like disclinations, which is something that will give you Gaussian curvature. Okay, so for example, this just shows you what we've already looked at already, the sheets and stuff like that. So this, for example, is negative Gaussian curvature from a disclination. This is negative Gaussian curvature from a series of dislocations, or dipoles if you like, which are put here at a certain distance between them, okay? And you can tell just from these lines here that I'm diverging, but I'm not as diverging as much here, which means that when I have an end to this polarization, I get polarization charge there, and it's a fraction of the charge I have over there. This is not the fractionalization I'm talking about. But I can make, therefore, negative curvature, okay, much more gradually than I did over here with the disclination. If I want to do something which has no strain whatsoever, I can do it like this. I can make these steps like I showed you before. Here's a step. This is a 5. That's a 7. That's a 5. That's a 7. That's a 5. That's a 7. So here they are equally spaced, and here I'm changing the spacing. So just as we were doing this, I'm jogging along in Manhattan, and I see this. This is the most beautiful skyscraper in the world. This is the Chrysler Building, okay? So I look at this, and I've been thinking about these problems, and so I take out a card and I hold it up like this to look at the edges and stuff like that. And then I take a picture like this, and I measure. and this spacing, this spacing, this spacing, this spacing are equal. And if you look at these guys, they give you a pyramid with no Gaussian curvature. But you look at the top two, and the spacing is bigger. And that's a gradient, and that gives this cusp, which clearly has negative curvature on the top of it, right? And my biggest achievement of 2010, is I actually got a picture of the Chrysler building published in Nature. Like that. Okay. Once you know this, and you put in the derivatives of the polarization charge, now you find instead of having this diotic, this rectification type behavior, now you find that in fact you get a line here. It's actually kind of cool. What actually happens is if you look at the integrated Gaussian curvature from a dislocation, it's pi over 3, you can figure out from looking at the curvature of the object how much area should that be. And the real thing that happens in terms of whether you get pleats or whether you get disclinations is whether the boundary of the region that corresponds to this integrated area of Gaussian curvature hits the boundary or not. If it hits the boundary, you get pleats. If it's inside the boundary, you get disclinations. So that's kind of neat. Okay, now, so far, we've kept the number of particles fixed. Now what we're going to do in the last couple of slides, before I get thrown out, is show you what happens when you add a particle. Okay, so typically, when you add a particle to a crystal, it's supposed to go in as an interstitial. It goes in between the lattice sites. An interstitial is supposed to be completely innocuous. It has no topological charge, it has no Berger's vector, it has nothing. Okay? If you strain the crystal, you shouldn't even move it. Okay? All it's supposed to do is diffuse around. So here's adding one to a flat surface. And sure enough, in a flat surface, what it does is it goes in interstitially, and if you like, it makes 2 or 3 opposite dislocations. So there's no topological charge, and the Berger's vectors add up to 0. Okay? That's what it's supposed to do. And you can look at this for a while, and you can just see it diffuses around, and sometimes it's 2, and sometimes it's 3, because okay. So that's what happens, and it just stays there. It's innocuous, it stays there, and it doesn't do anything. Now the question is, what happens if you do it on a curved surface? Okay? So here you go. This is a laser, a tweezer holds this here, and you approach the surface, and you see what happens is it goes in, and everything sort of changes around. It's not clear where it is. Again, it's a problem of looking to see what happens by triangulating. So here what happens is you see it goes in, and it creates 3 dislocations, and there's a scar over here, and it just gets absorbed in the scar. That's not so unusual, right? It only happens on the curved surface, okay, because you have to have the disclinations there, and that means you have to have some strain field, and the strain field acts on these to move them, to essentially absorb them. On a flat surface, you don't have that. Okay, so that's one thing that happens. That happens most of the time. Here's another one. Now, if you look at this just before I add the particle, you look at this region of space, okay, and there's just a hexagonal lattice there, a perfect hexagonal lattice. Here's the guy we're adding. Aside from that, it's a perfect hexagonal lattice. You add it, you add it. Come on. And it goes in, and things rearrange, and you note again, this region of space is just a perfect hexagonal lattice again. What happened this time? Okay, watch it, it's over here. This time it goes in, makes 2 dislocations, and one goes there, and the other one goes there. Where's the particle? What happened to the particle that I added? Okay. Well, of course, the particle's there. It's one of these guys, right? But if I look what happened to the extra density that I added to the system, okay, half of the density went that way, and half of the density went that way. And it's perfectly right, right? And this is the same thing that happens in solitons. It's the same thing that happens in domain walls, in crystals. And it's completely a classical effect, right? And it simply has to do with the fact that the difference in density is this guy has the same density it had before. It's just a nice hexagonal lattice. But the density over here and the density over here in these scars, in the disclinations and the scars, is different than it was before, and it's different in the crystal. And that's where the particle is, that's where, if you like, the density of the particle is gone. So we've really fractionalized the particle in this case. In the conventional way that you do in quantum mechanics when you write down, solitons or density waves or whatever. Okay? It's just here, it's completely classical. And the same thing happens, I should say. This is actually Mark Boeck's plot of what the strain field, the energy in the strain field is when you do that. Again, it just fractionates into these two. That's the strain energy. And I should just mention, actually this came out, oops, where am I? This came out last week, I guess, something like that. It also happens with negative curvature. Okay, so I'm done. I should give credit to William, who I gave credit to before, and also Mark, who's responsible for a lot of the theory that we've been doing on this. And there's all sorts of stuff to be done with this system that we haven't even done yet. We haven't yet really looked at Morse's domains like we should. There's 2D melting on curved surfaces, which is something that nobody's investigated yet. Oh, well, there's all sorts of stuff that we can do with it. Okay, so thanks. I want these back, all right? I want them back. Yes. The polydispersity, I mean, it's an interesting question. They're essentially uniformly charged to only about 5%. Okay, so the charge, the charge differs by about 5% in them, which you think would mess things up. But since they're screened, the screening takes account of a lot of that. Right? So if they're overcharged, you have extra ions around from the other guys which help to screen it. Nonetheless, it's surprising to me that it works so well, despite that. You can make, early on, what we tried to do is to take, but we haven't done that with, that's another thing we have to do with this. With a different charge system, we mixed different charges, and we shook it up to see if we could get a glass. And we ended up with a glass, but it really wasn't a glass because over a period of maybe a month, it actually went and made a compound, right? So we just took spheres of two different charges and mixed them together, and initially you get something with no Bragg scattering, right, but is rigid, and then a month later you start seeing Bragg scattering, you can identify and figure out what the crystal structure is. But these guys, in 2 or 3 dimensions, may form a glass. It's not really known whether a Vigner glass exists yet or not. About 100 electron charges.
So you really made me think that I would love to play with these systems, but I only have kind of a computer. So how hard is to simulate these things? If I just want
how hard is to simulate them? It depends what you want to simulate. The answer is, if you go to Mark Boeck's website, he has lots of simulations there, so do other people, and it depends what you want. So, for example, as usual, simulations lead you and stuff like that, but they can't do everything. For example, this movie that I showed you here, okay, the only thing wrong with this, because it pretty much shows you the effect, is this is a, what are these called again? I forgot the name of them. It's a sphere which has the 12 pentagons in perfect icosahedral symmetry, okay? If you change the number of particles on the surface, you won't end up with that. You still end up with 12 pentagons, but they won't be, they'll be moved off. If I take one out, I'm going to change the configuration. Moreover, with lots of particles, you get scars. So the time it takes for this system to equilibrate is longer than Mark can wait, even though he's doing simulations for a long time. So what he does is he makes an artificial system without scars, so it's not equilibrated, but with the particles, with the 12 pentagons in the right configuration. So topologically, it's correct, but energetically, it's not correct. And then he adds another particle and sees what happens. So the simulations are very useful, okay? They direct what happens, but they actually don't get the ground state. I should mention, it's not clear that we get the ground state either, right? It's not clear that our system, the experimental system, equilibrates. But my guess is it's got a better chance than that system. Yep.
At the beginning of the talk, you talked about hard spheres and
Yes.
the glassy phase in a region where the equilibrium phase, as I understood it, was crystalline.
Yes.
Is the glassy phase related to topological defects, which don't relax?
So in this case, it isn't, because they do. But I should just say the following. Let me see. I can do something. I think I can do something quickly, I hope, which may be a better answer to your question than just words. View graphs, balls, public lecture, Okay, so we did a lot of work on hard spheres, as well as these guys. So there are great experiments that have been done on great papers and stuff that have been done on these hard sphere systems. Okay. Bernal did stuff, the latency comes in, that's not what I want, that's not what I want. There's a great experiment that was done by this guy, Stephen Hales, in 1722. What he did was to do random packing, okay? He took peas. I love this experiment. Okay, so you want to know something about random packing of spheres, okay? This guy's a botanist, okay? So he takes a canister, he pours water in, pulls the stopper out of the bottom, he finds out how much water filled the canister, okay? Puts the stopper back in, puts peas in, shakes them up, pounds them, okay? Pours water in, drains out the water, measures how much water's in there. He knows how much volume the peas took up. Okay, this is an easy experiment. I would think of this experiment, okay? Then he does an experiment that in my wildest dreams I'm not smart enough to come up with. Puts the stopper back in, fills it back up with water, puts the lid on it, and cooks them, okay? Cooks the peas. Now, you cook the peas and they swell, okay? When they swell, you can take them out and you can count the number of neighbors. And you can find the coordination in neighbors, right? It's amazing. You even get second neighbor correlations because you see where two guys are around one pea, right? So I love this experiment. So I assigned it to an undergraduate. I was at Princeton. Undergraduates had to do a senior thesis. I assigned it to a student as a senior thesis. So he tried the experiment. Didn't work. Peas didn't swell. We got the book. This guy wrote. He was a don in one of the colleges in Cambridge. He wrote a book about this. We got the book. We found the type of peas. Okay, we got those peas. We cooked them. They didn't swell. Okay, so for some time we were thinking he just made the experiment up. Okay, but Sam Edwards, who was, it turns out, in the same college, said, well, you know, peas have been bred not to swell over the past couple of years. Anyway, which is nonsense, of course. Anyway, the student had to do his thesis, so he did Israeli couscous. And they do swell. And now you take them out and you look at them. And one of the things that Hales, who did this, said He said just what you said, Morris. He said, if you have the random packing, if you look at these guys, you'll notice that when they come out, several of them have five-sided faces, right? And if you have five-sided faces, you can't make a crystal. Five-fold symmetry is not commensurable with having a crystal. Why? Because if you have a crystal lattice, the easiest way is, if you have a crystal lattice, then if you have a lattice point, at a certain vector, you have to have one minus that vector, right? That's one of the properties of a lattice. Of course, if you have a pentagon, that point, there's nothing in the inverted point over there. Okay? So if you look at these, a lot of them have five faces, right? And so one of the ideas was that if you make something that's randomly packed, okay, you frustrate the crystallization because of these guys. Now, it turns out he wasn't quite true, because you also see that there are many six faces as well, right? So it's not completely true. What Hale said is that they were icosahedral, which really frustrates you in 3D. But in answer to your question, people wondered about that, okay? But that doesn't seem to be the answer in this case, because, for instance, there's lots of room for them to rotate around even if you're at 58%, right? But it's a good idea. It's a good idea. And it's been a lot in the literature that random close packing would do that. But isn't that a great experiment? This is an unbelievable experiment. Not my students, but Hale's, right?
Well, I think with this enthusiastic answer, we can close the colloquium, and thank you, Paul, for visiting us.
Yeah.